Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on evaluating the Bessel function of the first kind. And we are finally going to look at what is the most efficient way of numerically calculating this non-primitive function, this complicated Bessel function of the first kind. All right. And to remind you again, this Bessel function is one of the two solutions of the Bessel ordinary differential equation. This nu is called the parameter of the Bessel function or the parameter of the Bessel equation, and x in general could be a real number, positive, negative, and also it could be a complex number. So we are going to look at all these cases. So as I said before, the most efficient way of calculating some function like this Bessel function is through power series. So in order to do that, if you try to look at the Bessel equation and try to one of the methods for solving a differential equation is to represent the solution as a power series and then put the power series back into the differential equation and try to balance out the equations. Typically, you end up with a recursion formula for the coefficients, and in the case of Bessel functions, you end up with this. And the assumption here is that the x is a small number, right? Let's assume that it's a real number and its magnitude is small, all right? And we end up with a series from k from 0 to infinity, minus 1 to the kth power x over 2 to the power of nu plus 2k, k factorial gamma of nu plus k plus 1. So this is a gamma function, and we look into what this function is, all right? For integer values of nu, gamma of 1 plus nu is nu factorial, if nu is integer, all right? But even if nu is not an integer number, we can calculate this gamma function. And we also can calculate x over 2 to any power, so it doesn't matter if nu is integer or not. So gamma function also doesn't care whether or not nu is integer. So this representation is valid for all nu, integer or non-integer values of nu, even positive or negative values of nu, right? As long as nu a real number, this representation works, all right? Now it turns out this series is actually pretty good in evaluating the Bessel function of the first kind for any x number that is less than 30. So if x is real number, it can be between minus 30 to 30, and it works fine, all right? But the fact here is that this series actually also works for complex numbers as long as the magnitude of the x as a complex number is less than 30. So as long as the magnitude of the x is not very large, this series also works for any complex number. Again, because gamma is evaluated at a real number, we have this k factorial, which is fine. And then x over 2 to nu plus 2k, we already know how to raise a complex number to some power. All right, so this representation is valid even if the x is a complex number, and it's also, as I said, is valid for any value of nu, positive, negative, integer or non-integer, all right? But I mean, this is a polynomial. Although the powers could be non-integer, this has a format of polynomial. And if you recall, in polynomials, we said that instead of raising x to some power for each term and then adding them together, we use a clever way of reorganizing the terms, and it was called the Horner's method. So it was the most efficient way of calculating a polynomial. If you don't recall what the Horner method is, I'm going to go back to our lectures on polynomials. Let's see if we can find it here. So polynomials, we said that Horner's method is the most efficient way of evaluating a polynomial. And in polynomial, all the powers are integer numbers, but the fact is that even if it's not integer, we can always some sort of put them in a clever way, right? And the clever way for a polynomial was to start from this last term, a n minus 1 plus x a n. It has one multiplication, one summation, and then do a recursive calculations. So we get the result, multiply by x plus the previous index a n minus 2, get the result, and repeat, right? So we end up with only n summations and n multiplications, which is very good. It's very clever, and this was the most efficient way of evaluating a polynomial. Now for this power expansion or power series that represents the Bessel function, the same situation applies, but we have to be a little bit more clever because we have that gamma function in the denominator. So it turns out if you play with this series, you can write it in this fashion, and it's very similar to the way we're doing with Horner's method. So if you look exactly or look closely to what's happening here, then we end up with a leading term, which is 1 over gamma of 1 plus nu. So gamma function evaluated at 1 plus nu, x over 2 to the power of nu, and nu could be integer or non-integer. And the key here is that we have to calculate this term only once. This is our leading term, right? So we calculate this, we put this aside, and then we have to go and calculate the rest. And the rest has been put in this a nice way, which basically, again, similar to Horner's method, we start from the last term. Let's say we want to calculate nth term, or from k equals 0 to k equal n, right? So each term in this way of writing is x over 2 to the second power, all right, raised to the power of 2, divided by some number k times k plus nu, all right? Now the cool thing here is that we have to calculate, we only need to calculate x over 2 to the second power only once, because all these terms have x over 2 raised to the 2 power, right, raised to the power of 2. And that's very interesting, because then we calculate only x over 2 to the second power once, and then the rest is just calculating these terms, 1 over k times k plus nu, for k from 1 to whatever number n, all right? So eventually, for if x is small enough and k becomes large enough, we have x over 2 squared over k times k plus nu, and we subtract it from 1, right? So the nth term is 1 minus x over 2 squared divided by n times n plus nu. So when n is large enough and x is small enough, we can ignore that compared to 1. So we can always say that if I want to calculate for n terms, I can basically ignore the last term and start from 1, and then recursively calculate the terms, okay? So this is how we calculate that, and we can write it in a nice way in terms of a sequence, all right? So when x is, we said that this, based on how many terms we keep, this series can actually work for relatively large numbers of x, for example, x 20 or 30. But when x is really small, let's say less than even 1, obviously the approximation of the j nu of x is just the leading term, 1 over gamma nu plus 1 times x half x over 2 to the power of nu. And this is called the small argument expansion of the Bessel function of the first kind, j nu, all right? And this typically happens in all sorts of engineering and physics problems, especially when we deal with waves in a specific case, such as a cylindrical structure. So power series, as I mentioned, also work for complex numbers, because there is no restriction here that x should be real. Unlike the previous k that we had, and we said that when we calculate based on this integral definition, if alpha is not an integer, then we end up with this integration from 0 to infinity of this exponential, and the real part of the x, if x was a complex number, must be 0, so that this integral converges and gives us a number. But again, in this series representation, there is no limitation for x being real or complex. We just divide it by 2 and raise it to some power, and we already know how to do it for real numbers, positive, negative, complex numbers, no limitation on the real part being positive or negative, okay? And the other thing is that so as I mentioned, we calculate this leading term only once, which requires the calculation of the gamma function once, and then we calculate x over 2 raised to the power of 2 only once, And then we end up with n multiplications and n summations, so 2n, right? The rest is just a bunch of multiplying a bunch of numbers, 1 over k times k plus nu, and then subtract them from 1. So I hope you agree with me that this is just the most efficient way of calculating a function that doesn't have an elementary representation. We cannot represent it with finite number of elementary functions, okay? All we can do in the best case is to have a bunch of a finite number of multiplications and summations of numbers. And I hope you appreciate the fact that there is no complicated elementary function like sine or cosine in this series, right? In this part, which is a polynomial. So calculating this part is very efficient, and then we have to also calculate the gamma function once and raise x to some non-integer number nu. So if x is negative and nu is positive, we already know that the result is a complex number. So we have to be careful with that. So we define a sequence to calculate the sum, this summation, and then we also separately calculate this leading term, and then we basically get the most efficient way or the fastest way of calculating the Bessel function. For small arguments, we will see that for large arguments, we actually have to use another series representation, okay? All right, so the other thing about this power series for small arguments is that it exhibits a relatively fast convergence. So even if we don't need to use any acceleration on this series, so no Richardson acceleration. And first of all, Richardson doesn't work on this one because this has a 1 minus 1 to the kth power. So if we go back and review our lecture on sequences and series, we most likely need to the kind of transformation that we need to apply to our sequence is either the Euler transform, okay, or Aitken or Shanks transforms, okay. Most likely Euler is the most suitable one because you take a sequence and you convert it into series, and this minus 1 to the n term is there, right? So the terms are the series are alternating sign between plus 1 and minus 1. So we increase the rate of convergence, or we make the convergence faster by taking the nth difference, forward difference, and divide it by 2 to the n plus 1 power. But again, the series itself for Bessel function is fast enough. So 50 terms or 100 terms, we get a very good convergence. So we don't need to worry about accelerating it. All right. Okay, so how do we implement this? As I said, this is the expansion about the 0, x equals 0, right? This you can think of this as a Taylor series. And as I mentioned, it comes from assuming that this Bessel function, which didn't have any singularities, if you recall, we can write it in terms of k from 0 to infinity, ak x to some power k. Actually, we have to use something called the Frobenius theorem. In that case, this series, it shows that the x to the k power, basically the Taylor series doesn't have integer powers. It has to have some sort of non-integer powers, and we see that the powers here are nu plus 2k. So this comes from one of the theorems that are related to Bessel functions, the analysis, and you can just search it, Frobenius theorem. All right, so here's the code that we can write to calculate j nu. So nu can be any double number. For now, let's assume x is a real number. Positive, negative, doesn't matter, right? And then we extend it to complex numbers because basically the implementation is exactly the same. Every double x becomes a complex x number. Now the caveat here is that if x is a real number but is negative and nu is a double number, then we cannot raise a negative real number to a power of nu unless nu is an integer number. So raising a number like minus 1.2 to some real number like 1.2 doesn't give you a real answer. It always gives you a complex answer, right? So we have to be careful and check that condition here, that if x is negative, we have to switch to complex evaluation instead of real evaluation. But as I mentioned, we calculate the lead for any value of x. We calculate the lead term first, and we also calculate this x over 2 to the raised to the power of 2 once. I call it val here. And then I create a sequence that basically calculates all these terms recursively from the end. And for the nth term, I assume that when n is large enough, I drop the last term, so I start from 1. That's when my result is 1 in the beginning, and then this multiplies by val, which is x over 2 squared divided by I times I plus nu, and then it multiplies by the previous result, and then we subtract it from 1 and assign it to the new result. All right, so we calculate this, and then we reduce I. So that's why I have this for loop in a reverse order. So I starts from n and goes to 0, to 1 actually, I minus minus. So we start from the end, assume that the last term is 1 for relatively large n. And then we recursively go back. So I and then I minus 1, we take the result, val over reduce I by 1 times I plus nu, the previous result, subtracted from 1. And eventually we calculate this sequence at, let's say, 100 terms, and then multiply it by the lead term. That gives us the result of the J nu for a small arguments. So good convergence, faster performance than integration, actually much faster. Maybe I should write it here, much faster performance than integration. Works for real and complex numbers. So, but we're going to have a method just for real numbers and then switch to another method for complex numbers. And again, power series is the most efficient way of evaluating Bessel functions. All right, so let's head to Eclipse and try to implement this. I have already implemented it in this Bessel function class, but I'm going to create a dummy class and just show you how we can actually implement it. So let's call this dummy, or let's call it Bessel dummy. All right, and so I have a main method, but we don't need to have a main method. So what I'm going to do here, so we're going to have a sequence object, and this sequence, let's call it jnsec. All right, and then let's import it, and then we're going to basically have a gamma function. So I haven't discussed gamma function for now, but we will get to that. So for now, just assume that we have an object that can calculate gamma function. Gamma func, new gamma function. All right, and then I'm going to create a variable called last gamma. All right, or just gamma, let's call it gamma val. This basically calculates in our slides, if you look at it, it calculates this gamma 1 plus nu. Why am I doing this? Because I don't want to evaluate the gamma function in the method itself. Or basically what I want to do, I want to calculate, because if x is varying and nu is constant, I don't need to calculate the gamma function multiple times, right? Because right now in this implementation, gamma function gets calculated each time I call the method. But this is if calculating the gamma function is costly, which is definitely most costly than the for loop, because in the for loop, when calculating this series, it's a polynomial. So we just multiplying a bunch of numbers and subtracting them from each other. So the part of this implementation that may have the highest cost is calculating the gamma function at nu plus 1. All right, so let's have a constructor Bessel dummy, which doesn't have, it's just a default constructor. We can initialize our jn sequence here. Let's say n goes to double.nan. We can initialize it, doesn't really matter. And then I'm going to create our method double jnu, double nu, and double x. All right, so what happens here is that And also keep track of maybe last nu. So let's rename this to last gamma. So I want to, here I'm going to check that if I want to also import from math class all the static method. So import static. Okay. So I want to check ABS of nu minus last nu is less than 1 e negative 2. So if nu, what I'm saying here is that I want to check if nu has been changed. If I call the j nu repeatedly, is it the nu that is changing or is it x that is changing? Because if nu is not changing, I do not need to calculate the gamma function again and again for different values of x, because gamma function only depends on these nu values, right? Gamma 1 plus nu. So if basically if ABS of nu minus last nu is greater than 0.01, it means the nu has changed. So I want to calculate the gamma again, the gamma function, gamma func dot gamma at 1 plus nu, 1 plus nu, right? And originally the last nu is maybe we can double last nu is double dot mean value. You want to make sure that originally at least the last nu gets calculated only once, and this is our global parameter. Okay, and then let's do an x else. So if maybe let's also create another variable lead term, double, because we want to also double lead term. All right. So if gamma has changed, so I have to also calculate the lead term again. Lead term is actually I have to calculate the lead term always. So no matter what, okay, lead term is 1 over the last gamma times power half of x to the nu power, right? Now obviously we have to be careful that if x is negative, this is not going to work. So we have to have another check too. And then else if nu has not changed, and then let's also define another term, val, and the val is just basically is half of x times half of x. So maybe I can do it outside. Val is 0.5x times 0.5 times x. Okay, so we calculate this x over 2 raised to the power of 2, and then we check whether or not the nu has changed. If nu has changed, we calculate this gamma again, and then we calculate the lead term. If nu has not changed, then we just don't do anything. All right, we just use the last gamma. So then I need to calculate that sequence, jn sec n goes to what? So I'm using a multi-line lambda expression for the sequence, multi-line lambda expression. And here what I'm going to say, we have to calculate, so basically we start with the result, which is 1, and then for int I equals 0, I equals n, I greater than 0, I minus minus, result is 1 minus this val, which is x over 2 squared, val over times I plus nu, and this divided by the result from the previous guy. Now this is complaining because in our definition of the sequence, n was a long integer, it was a long variable, not an integer. So we have to do an explicit downcasting to n. saying that, okay, convert n to integer. So once we have this, and then we return jnsec, evaluate it at, let's say, 100 term and multiply it by the lead term. All right. So if so basically originally whenever we call this for the very first time, this last new should get calculated again. So we're going to also assign the last new to new here. And then originally we are going to assume that the new is changing, so we have to go inside. And then okay, so we have to also, in the sequence, we have to return the result. All right. So this for loop is pretty fast because it's just multiplying. We're not calculating even this val, which is a square function. It's just a bunch of I is changing, so a bunch of division, multiplication, and subtraction. That's all, and that's very fast. I mean, it almost takes no time, probably 1 millisecond for calculating 100 terms. All right, so this is it. So the caveat here is that does not work for x negative because of this power function. So we have to be careful, and we will see what we can do for that. All right. So I'm going to test this. So let's create a new class, test Bessel series, and let's have a main method. And here let's just have test1. All right. And here let's just have public static void test1. And here I'm going to create a Bessel dummy. Bessel equals new Bessel. All right. And then double array of x values, mathutils dot line space from 0 to 50 with 1000. Now as you see, 50 is outside the range of 0 to 30, so we expect to see some. So let's first go from 0 to 20. Let's see what happens. And double j0 is array func, and this array func is nothing but a for loop. I just put it inside this apply method, and we passed our function as a lambda expression so that I don't need to write for loop every time. All right. So we call our Bessel basically j new, and new is given, and then x is our t, and we're applying it to x, and we have to, so let's say set this to 0, and then you already know the routine. We're going to plot it, fig new fig dot plot x j0 with blue. Okay, let's just plot it. Fig dot, we're going to render it, fig dot show with an exit flag, true. All right. So let's run this to see what happens. So it just doesn't show the window, the plot, because I'm on a Mac, so I have to go and uncheck this VM argument. So as you can see, it did not work. The question is why. So let's double check here. So we are calculating new is 0, and then 1 over last gamma, and then we are going from n to 1 minus val times the result. Okay, and it looks correct to me. Oh, that okay, that's because let's see what is going on here. So instead of plotting, let's just check some values like sysout Bessel.jnew 0 and 0. okay, it gives us 0 times 10, it gives us 0 again. Lead term is last so it appears that so let's see what happens if we try to, I assume that it's because of this if statement, so let's see if this works. Yeah, it appears to work. Yes, so that works. So let's do two things. First, we try to calculate this gamma function each time. So I am going to set the timer, new timer from my mathlib class. All right, timer.start, and then actually we put it right after defining the array, and then timer.stop and timer.show. all right, so let's see how long it takes. 153, not bad, noting that we are calculating the gamma function each time, and this will go up higher if we go to a non-integer value. 155, still pretty fast. So our code works. And if I go to from 0 to 40, what you are going to see is that now we're getting the instability of the series. So the series works great up until about 30, 34 something. But then after that, you see we get this problem. And if I go even higher, you see that it really shows a very, very bad divergence. And it really doesn't depend even on how many terms we sum up. Let's say I sum up to 1000 terms. It still diverges after about 30 something. So let's go to 40 again. You see? So this series is good up until 30, and it has a relatively fast convergence. Even if I, for example, sum up 20, it should still give me a good result. Actually, it doesn't. So let's see 50. Yeah. All right, so if I go up to 30, even 50 terms should give me a good result. It does. But we're going to stay on the safe side and sum 100 terms, which is very good. So 100 terms is good. All right. Now my suspicion here is that this long time, 156 milliseconds, the price is this part that we are calculating the gamma function each time. I think I'm suspicious of that. So in order to test it, let's create another test. And public static void test2. all right, now in test2 I'm pretty much going to do the same thing here, but I'm going to create another Bessel method, jnew2, and in the jnew2 let's copy and paste this. all right, jnew2. Let's try to figure out how to deal with this thing. So we want to make sure that if so let's instead of assigning let's assume that originally new is 0. So let's assign this to 0, and then last gamma we just evaluate our gamma function 1 plus new, right? Last new. So by default, when we create an object, we are assuming that new is 0, and we calculate this gamma function. And then what happens here is that if nu is in fact if nu is 0, so I guess we have to also have an else statement here, and then do this last gamma lead term. We just have to calculate the lead term again. And we're not changing the last nu, right? So here, let's see what happens if we run this test 2. 5 milliseconds. And we're getting the same result. So as you can see, what happens is that when we're sweeping only the x values, not the nu, right? Because gamma function only depends on the nu, and what we see here is that the main cost of computation of this series computation doesn't absolutely have any cost, because it's just a bunch of multiplying a bunch of numbers and subtraction. It's almost no time, 0 milliseconds almost. So the cost mainly comes from calculating the gamma function. And again, as you probably can guess, gamma function is also evaluating the value, the function based on some power series. But then here I'm sweeping from 0 to 30, 1000 points, but nu is not changing. Nu is 0, 1 or whatever number. So I need to only calculate the gamma function only once, according to this very clever factorizing the series, right? This is an extremely clever and efficient way of factorizing this power series. And once we do that, we only calculate the, basically we keep track of whether or not this nu is changing when this method is called, jnu is called. All right, so let's just maybe rename these to jnu and delete the previous jnu. All right, and I assume we actually don't need to calculate the, I mean, we can just assign it to last gamma, and when nu is 0, the value it evaluates the gamma function, returns a value of 1, so we can test that too. Yes, so it takes only 5 milliseconds to calculate this power series for x from 0 to 30, 1000. Now let's obviously compare with our integration equation. So public static void test3, everything is basically the same here, but I'm going to create a Bessel function integration object. All right, so in Bessel function we implemented jn, right, for integer numbers. But all right, so let's run test 3. So keep this 5 millisecond in mind. Let's see what happens. We have 48 milliseconds, so we are using the power series, we are down by a factor of almost 10, from 50 milliseconds to 5 milliseconds. That's a huge advantage of using power series, especially not just power series in this form, power series in this very clever factorized form, because the complexity of calculating this gamma function and this x to some non-integer value nu has been reduced only to calculating one time as a lead term. The rest is just a polynomial, which is very easy to calculate. Now let's see what happens if we actually switch to a non-integer value. So this jn, we still call it jn, but it's actually jnu. We can have another method jnu. For the previous definition with the integration, we have to use the other integral too, and that will add more overhead in terms of numerical efficiency. So let's see, 203. So if it was an integer 0, we had 50 milliseconds. Now that it's non-integer, we get 200 milliseconds. So it's a factor of 4 increase. Now I want you to notice what happens when we do exactly the same thing for our power series implementation. So for the integration implementation is 200 milliseconds. For power series, it's 11 milliseconds. So a factor of 10, 20 from 11, from 10 to 200. It's a factor of 20. It's an impressive improvement in terms of the accuracy, in terms of the speed of calculation. And pretty much every scientific library in any programming language you look at that evaluates the Bessel function, it always uses a power series. And that's the general approach for any special function. Even gamma function or other types of functions, we always try to use a power series. Now, as I mentioned, the caveat here is that this implementation doesn't work for negative real numbers because of this power method, power function, and we can test it. So I want to run test 2, which uses the power series from minus 30 to 30. 10 milliseconds. You see, it returns, because the power series from the Java math library, it returns non-values for negative numbers. But we already know that the correct solution should be a complex number. Now, if I set it to an integer value, the power series has no problem. This function power from the java.math library, math library in Java, it has no problem calculating for negative nu when nu is integer. So we should get the correct answer, yes. As you see, this is the J0 for positive and negative numbers. It is a symmetric function. J1 is anti-symmetric, so let's double check that. Yes. Going through the 0, it changes sign from positive to negative, so it's anti-symmetric. And as I hope you appreciate how fast this evaluation is, 1000. If I go to 10,000, it again doesn't take much difference. So this is the most efficient way of calculating Bessel functions for the small arguments. In the next lecture, I'm going to discuss another polynomial or another polynomial expansion or series expansion that we can use for large arguments, large values of x. Well, that is a little bit more complicated, and we see why it is more complicated for large values, whereas for the small values, it was a very simple power series. Now, okay, so what I mentioned here is that when this jnu, the nu parameter, is not integer, we end up with the fact that we are not able to calculate the negative parts, because we already know that the negative parts are not real numbers anymore. They are complex numbers. So what I'm going to do here, I'm going to create another method, jnu, and in here now we have complex. We are returning complex from our mathlib library. And we assume that this x is now complex. All right? Now what changes here? This val is now complex. The lead term is also complex. So I'm going to create a double. So lead term complex, val complex. And obviously these are going to be complex. All right? Again, this gamma function, we are evaluating at 1 plus nu, and the assumption is that nu is real, nu is not complex. So this doesn't change. So I have to change this to val complex, and obviously lead complex. All right? And then I cannot use the power function or power method from the java.lang.math library. I use the complex math library that I wrote. All right, and so let's import this also from our mathlib library. So now it has no problem raising a complex number to any power of real numbers, right? The same thing here, lead term complex, we also set it here. and complex math. Now obviously we have one problem, because now we have to use this complex value in our sequence, and then this result should also be complex, but then this sequence should also return a complex number. All right, but so far our sequence object is only defined for real numbers, right? It returns a double. So what we need to do, we need to define a complex sequence, which is everything is identical to the sequence, but all the return types are changed from double to complex. That's the only difference. So I'm going to have a basically complex sequence here. Complex sequence, jnsec complex. All right. And we replace this here. Okay, so we have to return the result here. All right, so everything looks fine. All right. So let's see what happens if we try to now calculate complex numbers. So let's create another test. Test4 and public static void test4. In test4, I'm going to pretty much have the same thing here, this one. Okay. And this one right now, t is the real number, so it's invoking the double x, this method, right? But then we want to invoke the complex one, so we go plus 0 times j, and j comes from our complex class, so import a static complex, all the static members. Okay. Then the problem here is that this apply method, this functional interface is supposed to be return a real number, so we are going to just go with our for loop. Complex, new complex, x dot length, and then for int I equals 0, I less and then let's define also the length, x dot length, I less than len, I plus plus, and obviously we need to also import this complex. j0i is basically here, xi. So x is still a real number, but then we're passing it as a complex, so the imaginary part is 0. Now if we plot this, it plots both the real part and imaginary part, and I want you to notice what happens when x becomes negative. See? And maybe let's turn the legend on to be more specific about which plot is real part. Fix the legend on. All right, and which part is the imaginary part. All right, so see what happens. And we are plotting j. Okay, maybe let's start with j0, right? An integer index, an integer parameter. So the imaginary part remains 0 even for negative numbers. Okay, but then even if we go, let's say j new at 2, the imaginary part remains 0. Okay, but as soon as we go to 0.7, for let's say 1.2 or 0.7 or whatever, anything that is not integer, non-integer Bessel parameter new, as long as it becomes, as soon as it becomes non-integer, then even we pass in a real number, when it's negative, the value of the Bessel function is not real anymore. It becomes complex, so it gains an imaginary part. Voila, you see? The imaginary part is 0 for positive, but as soon as x becomes negative, we end up with some imaginary part. That means the Bessel function is now a complex function, and the power series still works fine. Okay? So you see the duration is very good, 23 milliseconds.